Right, hello. Um, this is likely to be fairly short once again, but like last week. This is, just so you know, the last one of these that we'll do until we restart again in September. Um, so yeah, just so you know, this is the last one. You will get some homework in the next lesson, but we'll give you the answers with it, I think. I think that's the plan. So you won't need to hopefully come here and worry about it. Um, And so I'll just answer the few questions I suspect that we're going to get, and then that'll be it. So we won't do much else unless somebody has got stuff. Can you do questions 10 to 13 from the year 10 thing? Um, let's have a look at it. This was the year 10 thing, I believe, that we gave this week. Um, and let's have a look at it. Okay, so so again, it's good that you're asking these questions actually, because these are the few topics that we have not done from physics paper one. This includes some sort of radioactivity, it's sort of chemistry as well, this. But I will talk about it briefly, this particular thing, and how you answer a question like this. Scientists sometimes replace one scientific model with a different model. For example, in the early 20th century, the plum pudding model of the atom was replaced by the nuclear model of the atom. Let me just, because I have some time, open up something that will help. Okay, so, right. You know, hopefully, that this is what an atom looks like, or at least what you're meant to know that it looks like, which has a nucleus in the middle, protons, neutrons in the middle, electrons around the outside. However, when I teach this topic, the thing that I always ask people is, given that atoms are so small, atoms are very, very small. They're so small that we can't see them. They're that small. Um, Not even with a microscope and stuff, we can't see them. Given that they're so small that we can't see them, how is it possible that there is a picture of one right in front of you right now? Um, Because how do we know that it looks like that? And the answer is, I guess we don't know for absolute certain that it looks like this, but based on lots of scientific experiments over time, we've led to the conclusion that this is probably what it looks like, because this allows us to explain why things happen, like why fire burns or whatever, like various other things like chemical reactions. You can explain them based on this diagram of an atom. Now, about 100, 200 years ago, um, we thought that the atom actually looked a bit like this, which is called the plum pudding model. And there was one particular experiment that you are supposed to know about that somebody did, which led to us believing that this must be wrong, and therefore there must be something else. Okay, and that's essentially what this question is. Um, so what this guy did was he got a sheet of gold foil, as you can see here. Gold is a element on the periodic table, which means that it's made of atoms. That's what these things are. And what he did was he fired these positively charged particles at this gold foil, really thin foil. Um, and let's just go to this here. So these alpha particles, they're positively charged particles, they were fired at this, right? And given what they thought that the atom looked like at the time, as in this thing here, what they thought would happen was that they put a detector on the far side here. So they could see when those particles went through and where they hit on the other side. Um, and what he thought would happen, right? Because this is what they thought the atom looked like. They thought that the atom was like this ball of weak positive charge, like spread out everywhere, um, all um, spread out with these electrons stuck in the middle randomly. That's what they thought the atom looked like. And so, based on that, they thought that if you fired positively charged particles, because it's so weakly positively charged, nothing much should happen. Like they should probably just go straight through and not move too much and not deflect too much, because maybe one that came near an electron might move a little bit, but that's what they thought would happen. Okay, they thought the particles would go to the other side and move around a little bit and things would happen. But that isn't what happened. What actually happened was some of them did go straight through, quite a lot of them did go straight through, but some of them deflected loads like that way, and some of them actually went backwards. So what they decided based on those results was that this model can't work because they couldn't explain what had happened based on those results. And so they changed their theory of what an atom looks like, and it led to kind of where we are today. So I want to get to the point of this, which is um, how do I explain this question? You mentioned that. So explain what led to the plum pudding model being replaced by the nuclear model. So how did we get from where we were to where we are now? So you want to mention that there was an alpha particle scattering experiment. That's what it's called, this thing that I just explained. In which what they did was they fired alpha particles at gold foil. And then there's three things you need to make sure you mention here, which is most of the particles did still go straight through, as I was trying to show you here, but most of them did go straight through. Okay. Some of them deflected at very large angles. That was those ones here, right? These ones deflected like at a very large angle, more than they expected. And some of them went backwards, as I said. Some of them actually went backwards. And what that's led them to believe, okay, and this is the important bit of this, what they concluded from this was three things again. Firstly, I want to put it over here. Because most of them went straight through, they concluded that most of the atom is empty space because they just went straight through. Some of them deflected at large angles and some of them went backwards. What that led them to conclude was that the ones that moved so much could only move because these things were positively charged if they came across another very strongly positively charged thing. Because then you repel, right? Like charges repel each other. And so the ones that moved a lot or moved a lot much more than they thought or went backwards, the ones that came close to something really strongly positively charged, and that led them to conclude that that strongly positively charged thing must be the nucleus in the middle of the atom that we now believe it to be. So they concluded that there is a strong positively charged nucleus at the center, and that's why some of them moved so much. And also that the nucleus is very small because only a few of them did that. So it must have been very, very small. It's like all of the positive charge is concentrated right in the middle of the atom. So that was the main conclusion that if I just go back to this picture, here, the old model was that the positive charge is spread out like evenly throughout the atom. Whereas now we believe or know that all of the positive charge is bang in the middle, right, where all the protons are. So they're all concentrated in this nucleus in the middle. It's not like spread out everywhere. And that's essentially that um, question. Right, that was all number 10. 11, 12, and 13 I will do. 11, the national grid ensures the supply of electricity always meets the demand of the consumers. Figure 13 shows how the output from fossil fuel power stations in the UK varied over a 24-hour period. Okay, so what do we learn from this graph? Again, I always recommend you spend a moment looking at these things. So this tells you that at about 12 p.m. on Monday, we had this much power from power stations. And then around 4, 5 p.m. to 8 p.m., it seemed to have gone up a lot. Now, I suspect that's because that's around the time when people come home from work and school. So generally, there's an increase in output and demand for electricity. And then it starts to fall as we get later at night and people turn the lights off and go to sleep. And then it stays quite low throughout the night because everybody's asleep. And then as people start to wake up at 4, 5, 6, 7, 8 a.m., it starts to increase again. You see, that's what's going on here, right? Suggest one reason for the shape of the graph between 3 p.m. and 6 p.m. on Monday. You could say that is because people return home from work and school. That's why that there is an increase between, well, this bit of the graph here, right? There's an increase of people. That's when around the time that people come home from school. Um, then, gas-fired power stations reduce their output when demand for electricity is low. Suggest one time when the demand of electricity was low. Well, anywhere here, right? Midnight. It was down here. The demand was low. That's it. Easy enough. Um, and then the national grid ensures that fossil fuel power stations in the UK only produce about 33% of the total electricity they could produce when operating at a maximum output. So that's two reasons why. Okay, so what we're saying here is that if I've got a power station, each power station that we have in the country only produces about a third of what it could produce. So we don't like max them out. We kind of go, okay, well, this could produce more, but we're not going to make it do more. Why do they do that? Well, partly because they want to have some spare capacity. Like if something unexpected happens, or if one power station breaks down, another one can cover for it. Do you see what I mean? So if like one stops working, so we can have a spare capacity in case another power station shuts down. And also, it also preserves your fuel reserves. Remember, this is a fossil fuel power station. We don't just want to use up all the fossil fuel just to make loads of electricity, even when we don't need it. Surely you'd only, you'd reduce it when you don't need it as much. So it conserves your fuel reserves. You could also have said, um, to not make an unnecessary environmental impact. Um, Yeah, and also spare capacity to compensate for unreliable renewable resources. So we might be getting some electricity from wind, but as you know, it's not always windy. So we have to still get that electricity from somewhere. And so being able to increase a power station's output is helpful. Question 12. A student investigated how much energy from the sun was incident on the Earth's surface at her location. She put an insulated pan of water in direct sunlight and measured the time it took for the temperature of the water to increase by zero point 0.6 degrees. Sounds like specific heat capacity, this. Choose the most appropriate resolution for the thermometer to be used by the student. Well, you're trying to measure an increase of zero point 0.6 degrees. Resolution is essentially how many intervals there are on the thermometer. Now, you don't want it to change by one, so you only get one, two, three. What if it goes up by like a small amount? You're not going to be able to see it. So the answer to this question has got to be the smallest one because that's the only one that will easily allow you to see a zero point 0.6 increase. Even though that one doesn't work because it'd be zero point 0.5, then another zero point 0.5, so one whole. So you can't get into that zero point 0.6 is a bit tricky. Um, right, this is really easy, but the equation will energy, power, and time. Again, you guys are all going to get a um, equation sheet. You've got to find the one. Power is energy divided by time is one of the versions of that equation. Calculate the mean power supplied by the sun to the water. So we need to work out power. We have an equation for it. All we need is energy and time. There's energy, 1050. We need time, 5 minutes. But 5 minutes, we don't use minutes in physics equations. You need to convert it to seconds by timesing it by 60. So you do 1050 divided by 300, and you should get 3.5 watts. Calculate the mass of water the student used. Right. So, one little hint for you guys for when you come to do your exams next year. Um, when you see the word specific heat capacity in the question, there is only one equation that refers to specific heat capacity on your equation sheet. So obviously that's the one you're going to use. There are other things on the equation sheet that are repeated a lot, like energy is on there like 6 times, and power's on there loads of times, and current and resistance. There's loads of different equations involving these different things. So it does take a little bit of time to get used to that for those questions. But if there's a specific heat capacity question, there's only one equation. And I'll tell you what the equation is. It is energy equals mass times specific heat capacity times change in temperature. Okay, that's what it is. And so now they'll probably want you to do something. Um, oh, no, you can't do it. Oh, it says, no, sorry. Calculate the mass of the water. So we've already got the energy, which is 1050. The mass is what we're working out. Specific heat capacity we know is 4,200 from the question. Temperature change was zero point 0.6, right? So the one thing that I do say when it comes to these equations questions is that if your maths is okay, you should never get them wrong because you don't really need to understand what's going on here. You just need to put the numbers in the right place in an equation that you are given. That shouldn't be too challenging, I'd have thought. 1050 equals, right? The 4,200 times 0 0.6, I can tell you, you have a calculator, is 2520, and then the m is what we want. So to work out the m, we're going to do 1050 divided by 2,520, which will give you 0.417 kilograms. The student results can only be used as an estimate of the mean power at her location. Give one reason why. Well, it's only an estimate because we're trying to heat up some water, right? And even though we've insulated this thing, some water will still be lost to the surroundings, or some heat will still be lost. Not all of the heat is being used to heat up this water. So I think the easiest answer is there'll be some energy transfer to the surroundings still. And so you won't capture it on that thermometer. The thermometer's capturing 0.6 degrees, but you're not going to get it all straight away because some of it will be being lost to the surroundings. Um, um, Maisha, that meeting as well. Yes, I've seen it. So yeah, yeah, I've seen the email about it. Right, last question then. 13. This is quite complicated, I suspect. A student investigated the efficiency of a motor using the equipment in figure 15. Right, so we've got a motor, we've got a pulley that's pulling up some stuff a certain distance. He used the motor to lift a weight of 2.5 newtons, a height of 2 meters. He measured the speed at which the weight was lifted and calculated the efficiency. He repeated the experiment again to give one variable the student controlled. Well, presumably the height um, that we lifted it and the weight that we lifted. So we did this twice, but surely both times we did it, we lifted it 2 meters and we lifted the 2.5 newtons. So you can say the height lifted or the weight used. The height or the weight would be fine. Two reasons for taking repeat readings in an investigation. One reason for taking more than one reading is always to calculate a mean or an average, right? You can't calculate an average with one reading. You've got to do it multiple times. And also to spot or identify anomalies. If you do an experiment once and you get it completely wrong, something crazy happens, then you're not going to know if you've only done it once. But if you've done it 10 times, then the one that went wrong, you'll see because it'll be way different from all of the other results. So that's that. Here are the results. Speed and efficiency. Okay. Two conclusions that can be made. Firstly, you can see that because the graph goes this way, you can say the easier option, which is that as speed increases, efficiency increases. That's the first obvious thing to say. However, what you want to say is that it curves downwards, which suggests that it will reach some sort of limit. So you can say it, you see that it's not going straight line like that. It's kind of curving downwards slightly. So it will reach a limit. And that limit is going to be 100% because efficiency can't be more than 100%. But anyway, the graph will ultimately kind of do that and it'll tail downwards. But the easy mark is just to say that as speed increases, efficiency increases. Give the main way that a motor is likely to waste energy, it's likely to get hot, right? A car motor engine, you touch it, it's hot, right? That is wasted energy usually. So heating the surroundings will probably be the answer there. When the total power input to the motor was 5 watts, the motor could not lift the 2.5 Newton weight, stating the efficiency of the motor. How do you do that? Is that not zero? It's zero. Sorry, I wasn't reading the question properly. It could not lift them. If it couldn't lift it, then no energy's been transferred, so it's not efficient at all. Because efficiency is how much you've got out of how much you put in, essentially, but you haven't got any out. So essentially, it's 0 out of 5, effectively, because nothing's happened. You couldn't lift it. I think that's all I want to do. Because I'm just, as I say, the purpose of these last few is going to change a little bit next year. These sessions, they're going to be all a full hour long. Then I'll have to do it twice, once with younger and once with older. And then we'll take it from there. There might be a slightly different system of doing it because I don't want to do this Zoom link thing. There's a slightly different way of doing it through our website. It'll be a login for the website and I'll do it through that. But I think that's it. Assuming you have no other questions, I am going to stop there. And I'll say no more next week, but you have your normal lesson this weekend, and that'll be the end of it until September. So,